Welcome back to my course Aspects of Biochemical Engineering. Now today I think last couple of lectures I tried to discuss transport phenomena. As I told you that transport phenomena is very important that unit operation process that is involved in chemical and biochemical industries. Now this transport phenomena that comprises of transportation of the different transportation mechanism of the process, and this and three different mode of transport phenomena is there. One is momentum transfer, and there is mass transfer, and there is energy transfer or heat transfer. Now we already discussed the momentum transfer, which deals with mostly the flow of the fluid, and through the flow of the fluid we can have the mixing of the liquid, mixing of the solute in the liquid, and also it involves the mixing time determination. In the last lecture we try to find out what is the minimum power requirement for the minimum mixing time, that those kind of information we can generate from that. After that I try to discuss the heat transfer, or the heat transfer. Basically it is very important in the biochemical industry because it required the environmental parameter for the microorganism plays very vital role. One important parameter is the temperature, and as we know that the biochemical reaction mostly they are exothermic in nature. So exothermic means heat liberating, that that process that we have, and most of the biochemical process usually operated in between 30 to 35 degrees centigrade. So particularly when since we are in the tropical country, our ambient temperature particularly in the summer season is quite high. So we required a lot of cooling arrangement particularly during summer season, and for winter season we required some kind of heating of the fermenter to maintain the temperature, because those things is very that we determine on the basis of heat transfer, and this heat transfer also involves the sterilization of the process, because I told you that sterilization means that we are killing all the microorganism present in the liquid, so that our desired organism can grow in the particular media, so that we can get the desired product. So heat transfer plays very important role. In the last lectures I try to discuss the heat transfer, how we design the length of that cooling coil, and also the temperature of the outgoing liquid in the cooling coil. So those problem we try to solve in the last lecture. Now today I am going to discuss another very interesting topic, what you call mass transfer. And mass transfer, it is always required, usually take place the transfer of the mass between the phases. As for example, that we know that most of the microbial fermentation process, they are aerobic in nature, and aerobic fermentation process we required dissolved oxygen, because in the fermentation media, because microorganism can utilize the oxygen which is dissolved in the fermentation media. So that plays very important role. So how we increase the dissolved oxygen concentration, we pass the air through the media, so that the oxygen present in the air as it transferred in the liquid. So that part I say I am going to discuss today. Now first let me discuss that what do you mean by mass transfer. Now here you see that mass transfer basically it is the transfer, it is the net movement of the mass from one location, usually the meaning of stream, phase or fraction or component, to another. So I was talking about, suppose this is a vessel and this is a liquid we are sparging air. So air bubble is going out, this is air in, and so when it goes, then oxygen present in the air, that goes to the liquid. That is the so this is remain oxygen present in the gaseous form, gaseous phase, and it coming to the liquid phase. So this kind of example that we have. Then mass transfer plays important role in the aerobic culture, where oxygen is purged, downstream processing, and other downstream processing like crystallization. Crystallization, we know that crystal that crystal formation, that means from the soluble liquid that at low temperature the crystal formation take place. I can give a very typical, very easy the simple instance, that is the sugar crystals. We can, if we keep it at low temperature, then crystallization of the sugar that take place. Then we have distillation. There also we distill the liquid from one phase to other, that from we liquid to vapor and evaporation, etc. Mass transfer effect plays a very important role in the immobilized and wholesale system. This also I discuss when I discuss the immobilized enzyme and immobilized wholesale system. And I told you that particularly that in case of enzyme, suppose we are handling the soluble enzymes, and major drawback of the enzymatic process is that after the reaction is over, that enzyme remain and impurities in the reaction mixture. So you have to purify, you have to take the enzyme out from the reactor. That is again that incurred some additional expenditure. So by this can be avoided by using immobilized enzyme, because if you fix the enzyme on a solid matrix and pass the substrate through the column, your substrate will be converted to product. So you don't have to separate the the enzyme from the liquid mixture. But the problem is that as soon as you immobilized, the soluble enzymes will be fixed on the solid matrix, the insoluble solid matrix. So it is a heterogeneous system, and heterogeneous system, I told you that the heterogeneous system major factor that plays important role, that is the diffusion problem. So that the mass transfer effect is very important in the immobilization enzyme and the wholesale system. Now, what do you mean by molecular mass transfer? This is a very simple example I have given. The net movement of the molecules or atom from a region of high concentration or high chemical potential to the region of low concentration potential, like this. Suppose here some concentrated that solute is there or solution is there. So if you keep it, then slowly it is diffused uniformly throughout the liquid, like this. So this is kind of what you call molecular transfer that take place. Now Fick's law, we know this is used for explaining the how this mass transfer take place. The law states that the molecular flux of a species relative to a observer moving with molar average velocity is proportional to the concentration gradient of the species. So what is happening, that molar average velocity, what is the velocity? Velocity is the length per unit time. Am I right? So molar average velocity, that here actually that depends on the proportional to the concentration gradient of the species. Now A diffuse, let us take the example, A is diffused in a binary mixture A plus B, and then according to the Fick's law, the flux of A can be expressed like this: ZA is proportional to, this is the concentration gradient, and this is x is the distance, that that so this is equal to that d in dA in dAb is the constant what we consider as the diffusivity or diffusion coefficient. So ZA, that rate of flux of A, can be expressed at minus dAb dCA by dx. Now question, why this negative term is coming? Because concentration of the always movement of the solute, they take place from the high concentration to low concentration. That is why this negative term has come. Now this is the Fick's law. Fick's diffusion flux is positive by convection, and since the diffusion occurs spontaneously in the direction of decreasing concentration, the negative sign is incorporated. This is the high concentration and this is the low concentration. This is how the negative term has come. Now, diffusivity, that depends on temperature, like this, DAB is proportional to T to the power 3 by 2 by P. So, this is how this is gas phase diffusivity. Another is the liquid phase diffusivity, DAB equal to T by mu. This mu is the viscosity of the liquid, here is the P is the pressure of the gas. The role of diffusivity in the bioprocess is the micro scale mixing, solid phase reaction and the mass transfer across the phase boundary. So, three different things simultaneously take place, then micro scale mixing, then solid phase reaction and the mass across the phase boundary. Now, let us first discuss the convective mass transfer. The mechanism similar to the free convection heat transfer. I think the last lecture I tried to discuss the difference between the convection and conduction and the radiation with respect to extinguishing a fire from a water source. So, here that the mechanism is similar to convection heat transfer, in which the density difference causes by the temperature. So, in case of heat transfer we have temperature difference, that is the gradient, and here the density that is the gradient is the concentration gradient, here you use. The free convection mass transfer is the concentration difference create the density difference, and convective mass transfer is strongly influenced by the fluid flow field, that how liquid is flowing, that strongly I shall give you a lot of examples, so that this conception will be clear to you. Now, this is the first example I can give you, this convective mass transfer. Now, this is the sugar cube, you can see this is the sugar cube. We keep the sugar cube in two different fashion. One is this hanging fashion, you see that we just hang the sugar cube in a solution. Then what is happening, this there will be convection current, this is the concentration will go like this. This kind of convection current is the high concentration to low concentration, this will occur. But when and this the sugar cube is kept in suspension in water and natural convection occurs. But when it gives at the bottom, touching the bottom surface, then a small sugar cube rests at the bottom of the beaker, natural convection does not occur, because one side is blocked. So, natural convection will be affected by that. Now, convective mass transfer coefficient, how we can write the transfer rate is proportional to transfer area and driving force. That I hope that we understand that in suppose there is a liquid and the liquid there is a bubble. So, we want to, if you want to transfer oxygen, this gas to liquid, it depends on two factors. The one is that driving force means concentration gradient, and another is the transfer area. The more area, more will be the mass transfer. So, this is like this, the proportionality coefficient in this equation is called the mass transfer coefficient. So, transfer rate equal to mass transfer coefficient into transfer rate and into driving force. So, this is, and this can be expressed like this mathematically. If we consider the mass transfer of A, Na is equal to K. K is the mass transfer coefficient, K is the mass transfer coefficient, and A is the area, and this is the driving force that we have. Now, Na is the rate of mass transfer, that and K is the mass transfer coefficient, as I told you, A is the area available for the mass transfer, and this area always we express like this. What is this? That surface area per unit volume of the particular material, that that per unit volume, that how much is the surface area, and Ca0 is the bulk surface concentration of A, and Cai is the interfacial concentration always less than the bulk surface concentration. So, it is Ca0 minus Cai. Now, let us see how the transfer take place, mass transfer in the aerobic fermentation process, gas liquid mass transfer. Gas liquid mass transfer is important in the bioprocess because the requirement of oxygen in the aerobic fermentation. I told you this is the limiting factor as per the biochemical industries or microbial fermentation is concerned. So, this is the gas phase, this is the concentration of oxygen in the gas phase, this is the concentration of oxygen at the phase boundary between the liquid and gas, and this is the concentration of oxygen at the phase boundary in the liquid phase, and this is the bulk. Am I right? Let us assume A is the transfer from gas phase into the liquid phase, and the concentration of A in the liquid phase is CAL in the bulk and CALI at the interface I showed you before, and in the gas phase it is CAZ in the bulk and CAGI is at the interface. Then what is the rate of mass transfer A through the gas boundary layer is what will be there NAG, that mass transfer take place in the gaseous phase is Kg into A CAG minus CAI. Okay. And this will be, but in case of liquid phase the interfacial oxygen concentration will be higher as compared to bulk, because it is mass transfer take place from the gas phase to the liquid phase. So, NaL equal to KLa into CALI minus CAL. Mass transfer CAI and CALI, these two are in equilibrium and they can be related by using distribution coefficient from the distribution law. CAGI equal to m into that how much of that oxygen present in the gas layer, that means dissolved in the liquid layer, that is m is the distribution coefficient that we have. Now, rearranging the above equations, we will come across this kind of correlation. Na equal to that this Na into 1 kGa m by KLa is CAG m into CAL, and in case of other equation we can Na 1 by m kGa 1 by KLa into CAG m by L into KL. This equation we can derive from that. Now, this equation, if you look at this equation, that from this equation we can write that this whole portion, what we can write, this we can write 1 overall, that overall, this we can write this overall gas phase mass transfer coefficient Kg, that is capital Kga, not this is small kGa and this is capital, this is overall. Now, this will be equal to 1 by k small kGa by plus m by small KLa, but similarly overall the liquid phase mass transfer coefficient can be expressed, this is like this. So, we can write that we have this equation, that is the rate of mass transfer gas liquid system can therefore using the two equation Na equal to Kga CAG minus m into CAL and Na equal to KLa CAG by m, and on the basis of gas phase and on the basis of liquid phase, that we can express this equation in the two way. Now, mass equation are usually expressed using the equilibrium concentration. You can express as that MCAL equal to C dash AG. This is the equilibrium concentration. So, CAG by M equal to C star AL, that we can write like this under equilibrium conditions. Now, this equation can be rewrite in this form: Na equal to Kga. This is the overall mass transfer in the gas phase, overall mass transfer in liquid phase, CAG minus CAG star A. So, mass transfer in the has two cases. First case, if you look at when a solution is very soluble in liquid, for example, transfer of ammonia to water, the liquid side resistance is small as compared to posed by the gas interface, because where the solubility is more. then the resistance will be less. Therefore, gas phase resistance rate limiting is the kGa equal to capital kGa equal to small kGa. So, we can write Na equal to small kGa Cag minus Ca dash when your solute is largely soluble in the liquid phase. Now, in the second case, if A is poorly soluble in liquid, this is another case poorly soluble in liquid, as for example, oxygen in the aqueous solution, the liquid phase mass transfer resistance dominates. And there that we can write capital Kla equal to small kla, and rate of mass transfer can be written like this. So, that is that happens, that is controlling by the liquid phase. When gas is highly soluble, that controlled by the gaseous phase. So, this we can, the Kl is very important design for the aerobic fermentation process. And Kla we consider as the volumetric mass transfer coefficient. Now, oxygen transfer from the gas bubble to the cell, that can be has 8 different steps. Transfer from the interior to the bubble in the gas liquid interface. I hope let me show you the diagram, then things will be very clear. This is like this. This is the, you see, this is the gas bubble here. Am I right? This is the gas bubble. So, it is going, it is first layered, then it is this is the bulk of the liquid. So, then it goes inside and slowly is entered into the cell. This is the, again here you see this is the we have this is the liquid film that we have across the cell, and this is the liquid solid interface here, and this is the individual cells that present inside the microorganism. That is that how it occurs. Now, this is in case of cell when remain in a clump. Individual cells, if you consider, it comes like this. This is the individual cells. It comes. This is the liquid film, and this enter into the system, and individual cells attack like this. So, here this is considered as the gas liquid interface, and this is the liquid film that we have, and this is how transfer inside the cell. So, when you consider that these steps, so this can be written like this: transfer from the interior of the bubble. We can write the transfer of oxygen from the interior of the bubble to the gas liquid phase, and movement across the gas liquid phase, diffusion through the relatively stagnant liquid film surrounding the bubble, then transport through the bulk liquid, diffusion through the relatively stagnant liquid film surrounding the cell, movement across the cell liquid cell interface, and if the cells are in a flow clump or solid particle, diffusion through the solid to individual cells, and transport through the cytoplasm to the site of reaction. So, there are 8 different steps involved through which this transfer can take place. I want to give you a very typical example, that is how the Kla can be estimated in our laboratory. This is the method that is largely used, what we call dynamic gassing out technique. Now, what we do basically it is like this. This is the fermenter, this is the aeration we have. So, what we can do, we have a probe. What is this is called dissolved oxygen DO probe, dissolved oxygen probe. So, it monitored, there is a monitor, it monitored that concentration of oxygen. Now, this concentration is expressed on the basis of percentage. The scale is 0 to 100. Now, how you do that? Suppose this is the media. You have taken media, and then what you do? You spurge. Initially, you spurge nitrogen, sterile nitrogen. Then you take it out. Then you will find that dissolved oxygen concentration keep on decreasing, and a time will come when it will constant. That is that you set it 0. Now, then again you spurge. This is replaced by air. you sparge air, and you will find the dissolved oxygen concentration will increase. A time will come when it will be fixed, that will adjust to 100. So, when is 100, that corresponding to the saturated dissolved oxygen concentration. So, what I can, if you go through any kind of handbook, chemical handbook, you can easily find out at different temperatures what is the dissolved oxygen concentration in water. So, if you know the percentage, suppose 90%, then you just multiply it by saturated dissolved oxygen concentration, you will get the what actual dissolved oxygen concentration in the liquid. So, this can be done very easily. Now, here the experiment that we have conducted by using Saccharomyces cerevisiae, temperature 30 to 35 degrees centigrade, air sparged through the media, one fraction remain in the broth and certain amount of utilized by the cell's growth, and rest comes out from the fermenters. Now, rate of mass transfer will be what here? Rate of mass transfer, this is the volumetric mass transfer KLa, and this is C star is the saturated dissolved oxygen concentration, and Cl is the dissolved oxygen concentration at any time t, because any time t, that is that expressed as milligram per liter, and unit of KLa is the time inverse. Now, rate of oxygen consumption, how you can write that by the cell, it is the Rx, if we that if we considered that suppose if we consider the specific uptake, specific oxygen uptake rate, what do you mean by that? 1 by x DO2 by, that means gram of oxygen that utilized per unit time by unit concentration of the cells. Now, suppose in a particular liquid you have x is the cell concentration. So, how much oxygen, rate of oxygen consumption will be there? This into x, then x will cancel, you will get the rate of oxygen that is consumed in the mass. This is called oxygen uptake. So what when you use the any kind of microorganism and sparge air, we call the condition is the dynamic. Why is dynamic? Because one is what is the purpose of sparging? To increase the dissolved oxygen concentration, and what is the organism is using, microorganisms, they are utilizing the dissolved oxygen for the growth and metabolism. So, the two things simultaneously take place, that is why we call it dynamic. Now, this is the equation we can write. The rate of oxygen dissolution or rate of oxygen transferred equal to that rate of oxygen transferred minus rate of oxygen uptake by the cells. So, in a fermenter, this is a fermenter. So, two things simultaneously take place, oxygen transferred, one is O2 transferred and another is O2 utilized by the cell. So, the difference will get you the how much oxygen that dissolved oxygen concentration increases in the system. So, if you say the under steady state conditions, this should be equal to 0, because rate of oxygen transferred should be equal to rate of oxygen used by the cells. Now, this equation we rewrite in this form very easily, and Cl equal to we can write in this is like this. Now, here I want to point out that that in this that if you plot, I shall show you how you can plot that Cl versus this 1 dCl by dt plus Rx into x. So, what kind of plot you will get? Negative slope. This is negative, am I right? This is negative slope, and this slope will be what? Slope will be equal to 1 by KLa. So, the volumetric mass transfer coefficient we can easily determine if we have a slope. Now, I shall show you how you can do that. So, suppose you are carrying out the fermentation, am I right? You are carrying out the fermentation. So, let me go to the next slide, then I think things will be very clear. Now, this is the situation that we have. Suppose in the fermenter, or suppose this is a fermenter, you have media, you have cell in it. So, you put media, you have cell, and this is the starter you have, am I right? So, this is moving and this is air use sparging. So, what is happening that as you sparging air, so initially the oxygen concentration will decay, will decrease and then attain the plateau, and when is attain the plateau, then we put the air off. If we put the air off, then what will you put this you close, so you do not allow any air to go inside, then dissolved oxygen concentration will decrease. And why it will decrease? Due to the growth of the organism. So, and again you put the air on here, and when we put the air on, we should remember this should be above the critical dissolved oxygen concentration, critical DO concentration. Am I right? Why? Because what is critical dissolved oxygen concentration? If you write DO concentration and mu, and it is like this. Now, above certain concentration, this mu is independent of DO, and this is called critical. So, this value always should be this side, not this side. If it is this side, then mu will depend on the dissolved oxygen concentration. Then what you then you have, when you put the air on, then you will find dissolved oxygen concentration slowly increase and attain increases like this. So, this is the pattern we will get. Now, here if you draw a sample and find out what is the cell mass concentration, then easily you can find out QO2. What is QO2? That you know the specific uptake of the oxygen by the cell, you can easily find out. And here actually at different point you can find out that dCl by dt, because this is dCl, am I right? This is Cl. This is Cl. So, you can easily find out dCl by dt. If you take a slope here, any slope is nothing but dCl by dt. So, you can easily find out this slope. Okay. And then you have seen this equation, this you know, this you know. If you know everything, then you can always plot Cl versus this at different point you can plot, and then you can find out the KLa value. Now, this is exactly how it is done. This I told you, this if you plot with respect to Cl, you will get the KLa value. This is our experimental result in our lab that we carried out. We got these results, the cell mass concentration at 300 rpm. Then we find out the Cl, how the concentration of Cl that decreases with respect to time, that we can find out. This is just to find out the Rx value, that we can find out that specific oxygen uptake by the cells, we can easily find out from this. Then we plot this and we can find out the KLa value. You can see that we find out the value is coming about 0.0243 second inverse. In this particular lecture, we try to discuss about the mass transfer, and mass transfer plays very important role as per biochemical industry is concerned, because most of the biochemical process is carried out by the aerobic microorganism, where the dissolved oxygen plays the limiting factor. So, how the mass transfer take place, what is the mechanism through which the mass transfer take place. We talk about the gas film, we take to liquid film, how across this gas liquid film mass transfer take place, how it can be rate of mass transfer, how we can calculate, we find out. Then finally, we try to discuss the dynamic gassing out technique through which how we can determine the volumetric mass transfer coefficient. Thank you very much.